the session B of the general remediation track. Really want to welcome everyone. A couple quick announcements. So this is the last session of the day. So right after this, we will have the reception occurring for the posters. And then after that, you're on your own unless you're going to the top golf VIP event. So by invite only, I understand. So for those of you that will be attending that. So it's hard to believe that just a mere 2 days ago, I was Star-Lord, Guardian of the Galaxy. And here I am now, back in my non-superhero role, moderating the session as Chad Northington from Terracon. But we do have a great panel. These are now, henceforth, Guardians of the Earth. So we have Alyssa Warden with NREX, Gary Burke, Tersis, Mr. John Freim with REGENESIS, and Clint Noble there on the end with CDM Smith. So great lineup of presentations today. Dr. John Freim is going to kick it off for us. And one thing I do want to say is that we're going to hold questions to the very, very end. So not even after each presentation. I want to make sure everybody gets a good time to present. So let's have your questions reserved to the end of this, if you don't mind. So with that, Mr. Freim.
All right, thanks, Chad, for the gracious introduction. Like you said, I'm John Freim. I'm the Director of Material Science at REGENESIS, and I work a lot on the R&D and manufacturing of our colloidal products that are used in situ remediation. So today I'm going to talk to you more specifically about promoting bioremediation within permeable reactive barriers, some new materials and technologies that we've come up with, kind of advance the technology of bioremediation beyond where it is in the last 10, 20 years or so. So the overview, I don't know if everybody knows what a permeable reactive barrier is, but I'll just give you a little bit of background about the fundamentals, how they work, and the limitations where they might fail. Then I'll segue into our solid phase colloidal amendments, which we inject into the ground in injectable barriers. And then I'll give you a little bit of data on lab studies on this material, how it promotes bioremediation, and I'll finish off with the results of a pilot that was done almost 3 years ago, and we still have some good data going on it. So this is a sketch of a permeable reactive barrier. The barrier here is this dark area here in the middle. And the way these things work is that you install these it could be trenched, but we try to do injection using DPT. And the groundwater naturally advects through these things where it's treated. And hopefully, if you do it correctly, when it comes down gradient, it's going to be clean or at least better than it was coming in. So, groundwater advection does all the work, and then the chemicals do their thing as the water passes through them. There's really a couple classifications of these barriers. One of them is a reactive barrier, PRB, where you have contaminants that are degraded in the barrier, so it can be either chemically or abiotically using iron or something similar to that. Or you can also have a biological barrier where you might have mulch or EVO, some sort of a bioamendment inside of them. So that's a reactive barrier. On top of that, we can have what I consider to be a passive barrier. So it's still a PRB. I don't think anybody really uses the term passive reactive barrier, but if you put activated carbon, for example, inside one of these things, there's really no degradation. There's a lot of advantages to using carbon. It slows down the advection within the barrier so you can get the degradation to happen. But as of itself, carbon doesn't do any degradation. So really the best way to build these things is to have a combination of activated carbon or some sort of adsorbent in the ground combined with some sort of reactive mechanism where you can have combined absorption and degradation, and this will make our barriers last longer and perform better. So activated carbon alone, this is the plume stop material that's sold by REGENESIS. If you wanted to, you could probably trench in another activated carbon powder or frack it in potentially. But plume stop is colloidal. It's about a micron in size. Can be injected at low pressures into permeable zones, and it's actually a quite good adsorbent if it's applied correctly. So what we've done at REGENESIS is that Dr. Bernstengel in our European office He's come up with a one-dimensional model called plume force, where he actually uses the thermodynamics of carbon absorption or the isotherms and can kind of predict the behavior of how contaminants going through a barrier will absorb, how long they'll last, what will break through, etc. So this for this purposes of this talk only, I'm just going to do kind of a simple situation where we have a 10-foot wide barrier. So you got 10-foot cross section where the contaminants pass through. You know, a moderate groundwater velocity. You know, typical porosity, 25%. And we're going to assume that we have 1,000 ppb of TCE only, which is pretty representative of a down gradient plume. And this barrier, we can't actually turn on degradation and model it that way, but this is going to be totally passive where there's no degradation within the barrier. So let me explain what this plot is. So this right here is the location of the carbon within the ground. You see it's 10 foot wide, and the groundwater is passing from left to right. So this is time zero. This is the day that you inject the carbon into the ground, and you can see that within that, it kind of looks like a quantum well or potential well. Carbon's such a good adsorbent, it pretty much removes all the contaminant immediately from the aqueous phase. So you kind of have up gradient, the stuff has not passed through yet, up there, and then down gradient is not being affected as well either because this just went into the ground. So let's click forward on time a little bit. So this is at 1 year. And you notice you kind of have a step function here. And the way these things behave is that when the contaminant hits the front of the barrier, it sees the very, very first cross-section of carbon, and then it absorbs to it, then it becomes saturated. So then it basically can't absorb any more contaminants. So the next wave of contaminant that comes through is going to have to go a little bit deeper into the barrier to find fresh or unsaturated carbon. So in this situation, you can see that maybe about 20%, 25% of the barrier is quote unquote full of contaminant after about a year. We can kind of click through time, and there's 2 years. You know, it kind of advances about the same amount of distance each year. 3 years, 4 years, and then 5 years, you can see that we basically have a barrier that's failed. And we still have contaminants absorbed within the barrier, but they're saturated. They've reached their capacity where they can't absorb any more TCE in this example. And what you'll end up seeing is the concentrations down gradient, the same as they are up gradient. And this is a real thing. I mean, if you have a moderate to high flux, these things will last for a while, but eventually they'll become saturated, and it's not going to be the preferred situation. So how long are these going to last? Well, it really depends on the environment, and it depends on the contaminants that you're dealing with as well. You know, if it's a low flux environment like PFAS, let's say you have a low ppb concentration of PFOA, these things can last decades before breakthrough. There's just not that much contaminant that's going into these things, and they can hold a whole bunch of material before they break through, which is good because there's no really known in situ mechanism to degrade PFAS compounds right now. So we're kind of beholden to absorption. But luckily, in most instances, that it's going to be fine with a low flux environment. We get to a moderate to high contaminant flux, like CVOC's downgrading of a dry cleaner, for example. It can be months to years before breakthrough. You know, probably a good rule of thumb might be 5 years. Granted, the faster the groundwater is moving, it'll be less time, higher concentration, less time. And it's also contaminant specific as well. But that's kind of a good rule of thumb. If you want to have a 10-year performance, for example, in a plume with TCE, it's really, really a good idea to try to do some concurrent degradation with the barrier. What this does is that once the contaminants are degraded, for example, TCE goes to ethene or ethane, they'll desorb from the carbon and provide fresh sorbent sites where the incoming flux in later time frame can actually still be sorbed and not have saturation and breakthrough. There's, kind of two different general classifications that you can do within a barrier. One's abiotic, where you add iron or some sort of other chemical mechanism. And there's also biological, which I'm going to talk about here, where we put in bioamendments to promote anaerobic bioremediation within the barrier. In the real world, you probably use a combination of both of these. You'd probably put iron and a bio in at the same time, but just kind of for simplicity, I'm just going to deal only with bioremediation in this talk here. So let's look and see what's available. What can we do to put inside a carbon-based PRB to promote degradation? So I'm going to kind of do these on classifications. And the first one here, I realize the font's kind of small, but it's soluble amendments. So this would be sodium lactate, molasses, glycerol, etc. Sodium lactate's a great donor, right? It's probably the best soluble donor around. Works really, really well. It's water soluble. You can put it at low pressures, etc. It distributes well. It's perfectly compatible with carbon, but the problem is it's just not very persistent. It either burns out, it degrades away, or it actually would vec down gradient with your water. So that's the problem there. If you want to use a soluble amendment, you're going to have to do a lot of reapplications. Emulsions, that's kind of the most common bioamendment EVO products. And once again, they can generally be applied at low pressures. They distribute well. They have moderate to good longevity. But the problem is that they're not compatible with activated carbon. They're actually hydrophobic themselves, and they'll preferentially adsorb to the carbon surface, and that'll blind the surface from actually absorbing your contaminants. So that's the issue, that you really have incompatibility between these emulsions, which are otherwise good, but they just don't work with carbon. And you can also have solid amendments. There's cellulose derivatives, chitin. Don't smell that stuff after it's been in a drum for a while. Well, a lot of these bioamendments smell bad after years, but I think chitin, man, takes the cake on that. Problem is they're kind of big, right? They're tens to hundreds of microns in diameter, and we're talking about an injectable carbon here that's a micron that you can do at low pressures with decent distribution. These things pretty much have to be applied at high pressures, and they're just not compatible from an application standpoint. So they all have shortcomings. So when I started at REGENESIS in 2018, plume stop was still, it was a semi-mature technology, but there was obviously the need for a bioamendment to go with it. And who's Jerry Garcia? What a long, strange trip it's been. I'm telling you, man, this is a long, strange trip. And when I first started, the idea was to use coffee and to grind coffee down. And I still remember going to the brew house in the roll-off, shoveling spent coffee grounds out and then trying to grind them into like a micron-sized donor. First of all, the stuff went moldy. It smelled. It just didn't work. But it was a good idea at the time. But after several iterations, we come up with a product called Aquafix, and it's a fermentable organic that's less than a micron, that's fully compatible with activated carbon, that has good persistence. So that's the kind of cool laboratory photo there. It looks like kind of the yin yang, or the kung fu thing where you're mixing black and white together. That's actually truly Aquafix and plume stop being poured together into the beaker. It's solid. It's less than a half a micron. It's really small. This is truly a colloidal product. It does not settle. Or if it does, it's very, very negligible. We also have some fast release components in there to kind of kickstart remediation. We use sodium lactate, and you got micronutrients, yeast, B12, etc. But the thing that's really enabling about this, it gives you a really, really slow and steady release of organic carbon to promote bioremediation. So we'll start with a treatability study. This is a bottle study that was done in the lab in San Clemente. There's my coworker Sophia right there, who deserves a lot of the credit for the development of this material. Kind of a standard bottle study. And we started with 10 milligrams per liter TCE, which is a moderately high dose. And we dosed it with our Aquafix and the bugs. And we actually redosed it, respiked it periodically for 110 days. So this is what it looks like. For explanation, this is a control that was done in parallel without any amendments in it. So you can see we started off with maybe 75 micromolar of TCE and spiked it. And that's what the concentration would look like cumulatively without any sort of active degradation. And you can see we have a really, really good progression of contaminants here. I think the next slide shows it a little bit better in the short term down here. But we, spiked it, put 60, 70 milligrams per liter of TC in this thing in 100 days, it's still working. So this is actually a better graph, I think. So you can actually see your natural progression of your chlorinated ethynes as they're sequentially reduced. So you start off with TCE, which is green. It goes down, the cis goes up, and then you get a little transitory spike in vinyl. And presumably ethene. I'm sure ethene's there, although the equipment we use in the lab doesn't have a FID detector to detect ethene. So it's kind of your classical sequence of cycling through daughters that you'd see with a traditional donor, such as EVO or lactate. What's almost more interesting to me, everything works in a bottle, right? Has anybody ever had a treatability study in a bottle that failed? Yeah, probably, but if they do, you're not showing it at the conference, right? So that's good. It's expected. It certainly gives us hope to go forward. But this longevity experiment really kind of blew my mind, and I wasn't involved in this. I kind of came in. I was making the stuff and not in the lab. But what we did is we kind of compared the release profile of three materials. One sodium lactate, which is this line right here. One of them is oil lactate, which I think they use 3DME, but it's very equivalent to an EVO product. And then this little orange line at the bottom was the Aquafix. And what we did is that over almost 500 days, we actually measured the TOC that was given off by this material and try to compare how these things behave. And once again, I think the next slide shows this blown up, and you can see the Aquafix a little bit better, but it's kind of as you would expect here. The lactate you dose, at whatever here, 5 grams per liter, and it lasts for a while, but it really kind of burns out and goes to zero. And in this experiment, it took 200 days, which in the field probably would be a little bit less than that, but in a bottle, it's probably expected. The EVO product, started off here and kind of slowly burned its way out, which is, in itself not necessarily a bad thing, but that's just kind of the way that product behaves as it biodegrades. But the Aquafix here, we started off in these bottles at about 10, and 500 days later, we maintained this range of TOC between 10 and 20. So this is kind of proving that you're giving a very slow, sustained release of your organic compounds that are going to support bioremediation, but they're not going to burn out per se or overdose at the beginning. You're going to be able to get a nice extended release of product. We did some back of the envelope calculations based on this, and we're on a typical dose, you're probably looking at 10 years of reactivity. The most we have in the field is about 3 years. And the data is somewhat similar to this. It's not exactly the same. But another thing that's good about this too is that some people are worried about methane. Anybody here have sites where the regulators are methane the fear of it. Largely, I think those fears are kind of overblown, but it's a real thing. And if you have, 10, 50, 100 ppm of organic in your groundwater, the chances of having any problems with methane are greatly, greatly, greatly diminished. So this is a really cool study that came out, better than I expected, to be honest with you. So, pilot study. This site was done in Michigan in the year 2020. So actually, during COVID, I was in the lab, in the manufacturing facility on Sundays. Nothing better to do, right? We're kind of stuck at home, but so I went into there and made a couple thousand pounds of the stuff on my quote-unquote spare time. And we shipped it up to this site in Michigan, and there were two areas that were done. One of them was done co-applied with plume stop, and the other side was done just alone with the Aquafix alone. And for the sake of time, I'm just going to show you the site that we did the co-application with the activated carbon. It's a pretty fast-moving site, pretty high concentrations, and it was actually kind of daughter-rich. There's quite a bit of cis here. I think there was some LNAPL there that served as an electron donor over the years. So hard to see the font there, but you kind of get the general idea here. This is the PRB that was installed, 1, 2, 3, 4, 5, 6, 7 injection points. We had 3 temporary sample borings to look for product distribution and also some sampling. And we had our monitoring well here. It's about 10 feet down gradient. They did check this well. There wasn't any product in the well. So the application was done, and where we kept the amendments up gradient, and any sort of degradation that was observed was actually due to water passing through the barrier and being degraded within the barrier. So this slide here has got a couple things going on. One of them, this is the TOC, which is on the right axis. So we started off at about 1,000 ppm, and it did degrade slowly. So it didn't behave exactly like it did in the bottle. There might have been some natural TOC on site, or it's hard to say for sure what's going on, but we're still close to 100 milligrams per liter 25 months out, and this is actually about a year ago. And I got some more data last week, and it's holding steady right about there. The chlorinateds basically went away. This is kind of be what you expected, in a barrier with carbon. Here's before we injected. We had mostly cis with a little bit of TCE there as well. And first monitoring period, 1 month, very, very little left. So that's owing primarily to the carbon, I'd say. The carbon, absorbed most of the contaminants that pass through the barrier. But if we go through time a little bit, you can see here, this green here is ethene. So we, slowly removed our chlorinateds, a little bit of vinyl here in intermediate periods, which is actually a good sign. It means that it's actually working. And then after about 16 months, the only thing we had down gradient for the most part was ethene. Another way to look at this here, this is not the contaminants per se in milligrams per liter. This is the mole fraction of what we see down gradient. So it's not necessarily a mass balance, but it's kind of a relative numbers here. You can see at the beginning we had pretty much all chlorinateds, and with time this transitioned to mostly ethene as the barrier basically started working and it kept on going. In 2 years, with 3% cis, 5% vinyl, and 92% ethene. So that's indicative of good bioremediation. We did microbial counts here. Background was near zero. We measured both the halichoides and the vinyl chloride reductase. But within about 5 months, we saw really, really healthy and large increases in the microbial counts, and they're bounced up and around a little bit. But for the most part, they stayed steady and at concentrations which are consistent with effective biodegradation. So, in conclusion, I'm not sure why they put the marketing people on these slides, by the way. That's Dane and Kat. They're in marketing. They're not scientists, but I guess they look better than me. But anyway, Aquafix, it supports, robust CVOC bioremediation. By the way, I'm going to do a show and tell here. I did this with my iron product in my previous company. But I had my assistant, James, he was my Vanna White, or he would come and help me out with it. But picture says 1,000 words. So that's what it looks like. So that's, the real material, put it in water, self-disperses, and you basically have a nice, colloidal, organic, solid phase organic solution. We try to get optical microscope pictures of this stuff. It's just too small. And I don't have good access to an SEM, but that's probably the next step to actually show what it looks like, at the microscale. Being a PhD material scientist, I probably should have access to an SEM, but I don't know. I guess I'm out of that game a little bit. So it works. Long-term sustained release of TOC. We got biogeochemical data on top of this I don't have time to show that will show more evidence of activity. And the TOC release profile and back of the envelope calculations at a typical dose, we should be able to keep activity for about 10 years. So we will see. I'm not sure how long they're going to monitor that site before they rip up the wells, but we've got a job going in next week. We're putting in 40,000 pounds of this stuff. So that's, I would say, the first major full-scale application. There's been about, I would say, seven or eight jobs in the past year where we've actually put this stuff into the ground. And I thought that I had my coworkers on this slide, but maybe not. I want to acknowledge Paul Erickson, who's the director of R&D, who was heavily involved on. There he is. He's better looking than me, but what can you say? And he was very heavily involved in Sophia Wynn, who's a research associate in San Clemente, who did a lot of the work, including unsuccessful work, by the way, of making this stuff. I've been in this business for longer than I want to say. I've been doing material processing for almost 40 years. And of the things that actually were successful that went to fruition, this was the hardest project I've ever worked on, as far as number of failures, having to reboot. But I think we got something now that actually works really well, and it's unique. And if you want to buy some, you need to call your friendly REGENESIS salesperson, and they'll be happy to hook you up. And this doesn't have to be used with plume stop. This can be used standalone. You can mix it with iron. You can mix it with EVO if you wanted to. If you wanted to have kind of the short-term boost of EVO and the long-term boost of this stuff as well. So, all right, I am at 27 minutes, and we're just going to move on, right? Is that correct? All right, thank you, everybody. If you want to see this stuff, I'll leave it up here. You can come by the booth. I could probably drink it. But.
Yeah. Any volunteers to take a sip? Anyone? No?
I did drink my iron product one time. And yeah, well, whatever.
That's another story. Yeah,